Welcome to Naradar Academy. In this video, we are going to discuss about vector spaces and vector subspaces. Okay, let's start with vector spaces. The definition is, if we take a non-empty set V, then it is said to be a vector space over a field F if V is a abelian group with respect to addition, and for every alpha belong to the field F and V belong to capital V, alpha V belongs to capital V. See, here in vector space, we usually take one non-empty set with a field. Okay, the elements of this V are called vectors and the elements of the field F are called scalars. Okay, so for V to be a vector space, first of all, it has to be an abelian group with respect to addition, right? Then after that, you take any element alpha, any scalar from the field and any vector here. Okay, the product of the scalar and vector is again a vector. This condition has to be satisfied. Okay, then along with this, we have some more properties has to be satisfied. Alpha into u plus v equal to alpha u plus alpha v, alpha plus beta into u equal to alpha u plus beta u, and alpha into beta u equal to alpha beta into u, and finally 1 into u equal to u. If all these conditions are satisfied, then we say V is a vector space over the field F. Okay, right. So for vector space, first what you have to check? Abelian group with respect to addition, and then the scalar alpha and vector V, their product, the product is again a vector and it should be in your V. Okay, then this conditions has to be satisfied. Let's see some examples for vector spaces. The first one is R cross R is a vector space over R. R denotes the set of all real numbers here. It's a field. As we know, it's a field. So here in the field we have taken R, and in the place of V we have taken R cross R. That is the two-dimensional space. So the elements here will be of the form x comma y. Okay. So this is R2, isn't it? So clearly we know it is an abelian group with respect to addition, right? And then what about these properties? So if you take any scalar here from the field, then their product will also belong to R cross R, because everything is R only, no? So if you multiply a real number with this x comma y, again it will become what? It will be an element of R cross R. So this condition is also satisfied. Also, whenever you are talking about R, we are talking about usual addition and usual multiplication only, no? So obviously all these conditions will get satisfied, and hence R cross R forms a vector space over R, and this can be extended to any finite number, that is Rn is also a vector space over R. Rn means what? Its element will be n tuples, isn't it? So it also form a vector space over R. In general, how can we generalize this result? If we take any field F, what do you mean by field? It is an abelian group with respect to both addition and multiplication, isn't it? So if you take any field F, then Fn, okay, Fn forms a vector space over the same field F, right? Then some specific cases, this R cross R is a vector space over R, no? That can be rewritten in this way. C is a vector space over R. R cross R is isomorphic to C, no? What is this C? The field of complex numbers. So it forms a vector space over R, right? Then R is not a vector space over C. Here we have seen C is a vector space over R, but R is not a vector space over C. The reason is, here in the field, this is the field here we have taken, no? In the field you take one complex number a plus ib, and then you take one x here. Then what is the product of the scalar and the vector? A plus ib into x. That is not a real number. That will be a complex number only, no? That is not a real number. That doesn't belong to R. That is, this condition is not satisfied. What is this condition? For every alpha belong to F and V belongs to V, alpha V belong to V. This condition is not satisfied when we take R over C. Okay, so R is not a vector space over C, whereas C is a vector space over R. Okay, then the singleton set 0 is a vector space over any field. Okay, because this forms an abelian group with respect to addition, and whatever field it may be, if you take the product 0 into any scalar, it will again become 0. So it again becomes an element of V. So singleton 0 is a vector space over any field. Okay, then if f is any field and f of x, the set of all polynomials, so set of all polynomials over any field, that is also a vector space over f. Okay, right. Then the set of all polynomials of degree less than or equal to n, including the 0 polynomial, it again forms a vector space over f. Okay, right. Then the next one is, consider M2 of R. M2 of R is nothing but set of all 2 by 2 matrices over R. That is the set of all 2 by 2 real matrices. It forms a vector space over R. And then the set of all functions from R to R. Okay, functions from R to R is also a vector space over R. Then another one is Z is not a vector space over Q. Okay, Z is not a vector space over Q because the same reason. If you take any scalar here, any rational number here, for example, here I have taken 1 by 2 as a scalar, and here in Z you take 3 as a vector. So what is 1 by 2 into 3? 3 by 2, it's 1.5, that doesn't belong to Z, no. So Z is not a vector space over Q. Okay, right. Then if U and V are vector space over F, then W equal to the ordered pairs U comma V is also a vector space over F. Okay, right. Then let's go to the next definition, subspaces. Okay, subspaces means, suppose if we take a vector space and a non-empty subset from this V. Okay, V is a vector space. In that vector space, you take a subset W. If this W itself is a vector space, then W is called a subspace of V. Okay, the operation of addition and scalar multiplication should be same as that of V. You should not define any new type of addition or scalar multiplication here with respect to the usual addition that is followed in your V. With respect to those operations, if this W forms a vector space, then W is called a subspace of V. Okay, for verifying whether W is a subspace of V or not, it is enough if we check, take two vectors UV belongs to W and two scalars alpha beta. Then you check whether alpha U plus beta V belongs to W or not. Okay, if this, for every UV belongs to W, if alpha U plus beta V belongs to W, then this W forms a subspace. Instead of checking all the conditions, it is enough to check only this condition because all other properties are hereditary properties. Okay, if you check only this condition, that is enough. It will obviously become a subspace of V. Okay, let's see some examples for subspaces. Okay, if V is any vector space, then the singleton 0 and V itself, they are subspaces of V and they are called trivial subspace. Okay, trivial subspaces of V. And then consider this one, W equal to triplets A00 where A is a real number. This forms a subspace of R3. Can you see what is this? This is nothing but the set of all points in the real axis, isn't it? Only A, first coordinate is there, the remaining two coordinates are 0, that is x coordinate is A, y and z coordinates are 0. So this denotes the set of all points in the x-axis. This forms a subspace of R3. Let us verify. So for verifying whether it's a subspace or not, what you have to do? Alpha U plus beta V should belong to this W. So let me take A00, B00, be two elements of W. Let me check whether alpha U plus beta V belongs to the same W or not. So alpha into A00 plus beta into B00 is equal to what? Alpha A plus beta B00. So it again follows the same pattern, no? So what is the criteria to be followed for a member of W? The first coordinate should be there and the second and third must definitely be what? 0. First coordinate can be any real number. The second and third coordinate must be what? 0. So here also the same thing only, no? The first coordinate is what? Alpha A plus beta B. Second and third coordinates are 0. That means what? This again become an element of W. Therefore W forms subspace of R3. So here we consider the set of points in the x-axis, no? In the same way we can easily prove that the set of points in the y-axis and also in the z-axis, they also form subspaces of R3. Okay, right. Then next problem. Now this is another problem. W equal to set of all triplets of the form Ka, Kb, Kc where K is a real number. This also forms a subspace of R3. Again the same thing. Let us take two elements, two vectors from W. K1a, K1b, K1c, K2a, K2b, K2c. Okay, here look at the definition here. Be careful while choosing the vectors. Here A, B, C are fixed. Only K is varying over R, isn't it? A, B, C are fixed. K only varies over R. So how will you take two elements? K1A, K2, K1B, K1C, K2A, K2B, K2C belongs to W. And you take two scalars from R, alpha and beta. Then alpha into K1A, K1B, K1C plus beta into K2A, K2B, K2C equal to, what will you get? A into alpha K1 plus beta K2, B into alpha K1 plus beta K2 plus C into alpha K1 plus beta K2. Look at this number. See, this is some real number into A, comma, real number into B and a real number into C. That is what the pattern followed in W, no? So this is also an element of W. So that means what? W is a subspace of R3. Okay, then next example. W equal to set of all triplets A, B, 0 where A and B are real numbers. It's a subspace of R3. Okay, now what is this? These are, this is x coordinate and y coordinate. X coordinate and y coordinate. Z is 0 always means these are points on the xy plane. Okay, the set of all points on the xy plane forms a subspace of R3. Let us check. Let us take 2 points. AB0, CD0 belong to W. Then alpha into AB0 plus beta into CD0 equal to what? Alpha A plus beta C, alpha B plus beta D 0. Isn't it? Again this like what? This is an element in x-axis and this is an element in, sorry, this is the, that is what to say, every time the z coordinate is 0 means this is a point in the xy plane. That means it is a point in W. Therefore W is a subspace of R3. So again here this represents the set of all points in the xy plane. That forms a subspace. In the same way we can prove the set of all points in the YYZ plane is a subspace. Set of all points in the XYZ plane forms a subspace of R3. Okay, then next example. This is a matrix. W equal to set of all matrices, 2 by 2 matrices of the form A0, 0B, where AB are real numbers. This forms a subspace of M2 of R. Okay, see what is the property of this W? Only the diagonal elements, principal diagonal elements should be there. The rest of the elements should be what? 0. So let me take two matrices and alpha beta in R. Then alpha into the first element plus beta into the second element will form again the matrix of the same type, isn't it? Only the principal diagonal have numbers. The rest of the things are 0. So this also belongs to W. Hence this forms a subspace of M2 of R. Okay, right. Then the next one is W equal to AAA, triplet AAA, that is constant element where A belongs to R, is a subspace of R3. So you take two triplets like this, AAA and BBB. Then if you take alpha AAA plus beta BBB, what will you get? Alpha A plus beta B, comma alpha A plus beta B, comma alpha A plus beta B. So what is the condition for this element to be in W? All the three coordinates must be the same. Yes, they are same. Hence it's an element of W. Therefore W is a what? Subspace of R3. Okay. Then the next example. What is the next example? W equal to XYZ with X plus Y plus Z equal to 1. This is not a subspace of R3. Let us check whether it forms a subspace or not a subspace. See what is the condition to be satisfied? A triplet with sum of its coordinates equal to 1. So let me take two such triplets. X1, Y1, Z1, let me take it as U vector, and X2, Y2, Z2, let me take it as V vector. B2 triplets belong to W. So what is the condition for these elements to be in W? Sum of the coordinates equal to 1. So X1, Y1, Z1 equal to 1 and sum of X2, Y2, Z2 equal to 1. Now let me consider alpha U plus beta V. Okay, so I am getting it like alpha x1 plus beta x2, alpha y1 plus beta y2, alpha z1 plus beta z2. What is the condition for this to be an element of W? Sum of the coordinates should be equal to 1. So let me check whether the sum of the coordinates is equal to 1 or not. So if you add the coordinates, separate the alpha and beta terms, See, this is 1 and this is also 1. So finally what is the value? Alpha plus beta. But alpha plus beta need not be always equal to 1. No, it can be anything, because if you change the values for alpha and beta, it may get varied. So this element need not be in W. Therefore W is not a subspace of R3. Okay. Okay, right. Now let's see some important results about vector spaces and subspaces. Okay, right. The first one is intersection of any two subspaces of a vector space is always a subspace. So intersection is always a subspace, but the union need not be a subspace. So when will you get union of two subspaces as a subspace means? If you take A and B as subspaces of V, then if any one of this condition has to be satisfied, that is either A should contained in B or B should be contained in A. In this case only we can say A union B is a subspace of what? V. Okay. So for intersection no condition is required. Obviously intersection of two subspaces is a subspace. But for union either one should be a subset of the other. In that case only union will become a subspace. Otherwise the union is not a subspace. Next one. A plus B. If A and B are subspaces, then A plus B is also a subspace, and this is the smallest subspace containing both A and B. Okay, so this is a superset which contains both A and B, and this is the smallest such subspace. Okay, then the next one we are defining direct sum. Suppose if A and B are subspaces of V, okay, then V is called direct sum of A and B if first one V equal to A plus B, another one is A intersection B equal to 0. So what do you mean by this direct sum? That means you take a vector space V, okay, then you find two subspaces A and B such that their intersection is equal to singleton 0. Okay, and you check whether every element of V can be written as an element of A plus element of B in a unique way, right? So what are the conditions to be satisfied? Take one vector space, take two subspaces with their intersection equal to singleton 0, and every element of V, every vector of V should be written as uniquely written as a sum of an element of A plus element of B. If these two conditions are satisfied, then we say V is a direct sum of A and B, and it is written in this way: V equal to A direct sum B. Okay, so when will this be possible? When only it is a direct sum. Okay, right. Then let's see some more examples. A equal to triplet AB0 with AB belong to R. Okay, that is A and B are real numbers, and B is equal to 0, 0, 3, C with C belong to R. Okay, then A and B are subspaces, no, because this is points on the XOY plane, this is points on the Z axis. These are subspaces. What about the intersection? Only singleton 0. Okay, also for any element in R3 can be written as sum of these two elements, isn't it? AB0 plus 0, 0, C. So what can I say? R3 is a direct sum of A and B. Okay, right. Then next one. Consider these two matrices. A equal to set of all matrices of the form AB 0, 0, and B is the set of all matrices of the form 0, 0, CD. These two are subspaces of M2 of R, and their intersection is singleton 0, and every element of M2 of R can be written as unique sum of an element of A plus element of B. This is another direct sum. Another one is quotient space V by W, which is defined as W plus V for every V belongs to V. Okay, this is again a vector space over F with the operations W plus V1 plus W plus V2 equal to W plus V1 plus V2, and alpha into W plus V equal to W plus alpha V1. This space is called quotient space of V by W. That's all. Thank you.